So my name is Chris Eaton. I've been with the DB2 organization. I guess I should now say I was with the DB2 organization for 24 years, before it was called the DB2 organization, before it was called DB2 for that matter. And I've since, for the last 2 years, I spent most of my time focused on machine learning, artificial intelligence, deep learning, and power systems. So at first I was like, well, I don't know anything about AI, so let me start learning. And so what I've done is actually kind of culminated a bunch of my learning into this session. How many of you have had experience with any kind of AI? Machine learning, deep learning, built anything? Built any models? A couple? One? Two couple? Okay, so all of you have had experience with AI, whether you know it or not. Right? If you use Siri, well, you're using AI. If you get ads sent to you in your Gmail, guess what? That's all AI. They're all watching what you're doing and sending you ads based on what they think you might do. But actually taking your data that we are, I kind of think of all of us are guardians of the data, right? We manage the data, we organize the data, we clean the data. All that data is now extremely useful in all of these spaces. Right? There's a lot of other data that I'll talk about that is useful for augmenting the data we already have in our databases, but actually getting at this data is critically important. So what am I going to talk about today? Well, I'm going to talk about why artificial intelligence is so hot, and why is it so hot now? And it's not new technology. It's not, I shouldn't say technology. It's not a new thing. It's been around since the 1950s. But why is it hot now? So I'll talk a little bit about that. And then I'll talk about most of this time talking about AI terminology so that you can leave this room and someone who's talking to you about AI or machine learning or deep learning or some model they've built, you'll understand what they're saying. You know, maybe there's not enough time in an hour to actually get you to be able to build a model, but or create some artificial intelligence, but at least you'll understand what people are talking about, and then you can take that to the next step about learning how to actually do this kind of stuff. I'll talk about how it works. So understanding machine learning and deep learning, which are deep learning really a subset of machine learning. I'll talk about why that is or what that means in a minute. And then I'll also spend a fair bit of time talking about computer vision, because after spending 2 decades in databases, they're not so fun to look at. Let me show you my database. Wow, that's really cool. Let me show you how fast it runs. Okay, that's a nice, interesting thing. But actually one of the things I like the most about AI is it's actually practical, and you can actually see something useful out of it. So I'll give you a little demonstration at the end of AI vision, because that's the most visual one. I am going to do a couple demos at the end, so when I get to the demos, if you want to move up, I used to say, I could sit at the back because I had LUW eyes, but now I have ZOS eyes, so I actually need to move closer to the front all the time now. I have my glasses right here, but I'm standing at the front so I can see. But feel free to, I won't feel bad if you actually move up later on. Most of it's big picture stuff. So, what's the compelling reason for using machine learning? Well, all of these big companies use machine learning on you every day to try and, they're trying to influence what you're doing, right? We spent all of our careers working with SQL and asking questions of the database, and that's asking what's happened. How many units of this product did I sell last month? Okay, that's an easy SQL query, right? Run SQL gives me the answer. So SQL is a lot about what's happened already. We started doing some predictive work. There's been going on for a long time. SAS, SPSS, all of these are predictive. They're trying to predict what's going to happen next. When am I going to run out of cornflakes on the shelf? Right? So I can keep my supply chain moving so that I actually have cornflakes always on the shelf. So you're predicting. What AI is about is actually trying to be more prescriptive rather than predictive. There's a predictive component to it, but instead of just predicting what's going to happen, I want you to actually do what I want you to do. So Netflix wants you to watch a certain movie, or Amazon wants you to buy something along with the thing you're already purchasing. Right? And they're using AI to figure out what's the most likely next possible purchase for you. Or I'm driving down the road in my car, and my onboard navigation system says, hey, don't forget you ran out of cornflakes. I'll use that example again. And by the way, the store around the corner is going to add 30 seconds to your drive. And I'll reroute you there if you want. Yes or no? I click yes. And changes the directions to take me to a particular store. That's what that's what all these companies are working on, is trying to get you to do something that is helpful to you, hopefully, but also, it's a little bit creepy. That's the thing about AI. It can be a little bit creepy. And the way machine learning works is, it's not about, like we're used to, SQL. I write a query, I know what I want, I write the query, it gives me the answer. Right? So I'm building the algorithm to give me the answer. With machine learning, it's not like that. Some people say, I've seen some people talk about machine learning and artificial intelligence, and they say it's about software that writes itself, software that writes software. I don't like that idea. I can see where they're coming from, but I tend to disagree a little bit. Machine learning and deep learning and AI is really about looking for patterns in data. That's pretty much at the very core of it. That's exactly what it's doing all the time. It's looking for patterns, and then given some new piece of data, it'll tell you, based on the previous patterns, what it expects to happen. Given the pattern of people who buy certain products, I take your purchase and I say, okay, you're likely to buy this. Okay? Or given I get this all the time on my phone too. Hey, you just made a purchase at something. Is this really you? I get that from my Visa. Right? Visa will tell me, hey, is this really you? And I say yes. Because it's looking at, here's your normal buying patterns. Here's the normal buying patterns of all of my customers. This thing didn't quite match that pattern. Maybe it's fraudulent, because they want to catch the fraudulent transaction before it actually happens, right? They don't want to catch it afterwards. That's not as useful to them. So instead of writing code, you're feeding data into an algorithm that's going to go and then make some predictions at the end. Now, the making of those predictions is actually code. It's an algorithm. So that's why people say it's software that's writing software. I like to look at it as machine learning is software that's looking at patterns and making predictions. That's in the nutshell how I describe machine learning. Now, people say, code that writes code, that's, it's going to kill us all, right? What's it, Skynet's going to go in, or HAL, or someone's going to kill us all. Well, it's not the problem that, AI-powered robots are going to take over the world. The real problem, and the problem we're working on today, is automated decisions based on bad information, based on untrustworthy data or learning that was biased. There's a big push right now in understanding bias in AI. Let's say, for example, let me take an example of maybe I create some AI system that is going to tell you if you get a loan or not. You go to the bank and you fill out the online form or whatever with all of my information. It looks at all my background and it decides, am I going to get a loan or not? Well, it'll use AI algorithms, machine learning algorithms, to decide, am I likely to default on that loan or not? And that's going to decide whether they're going to give me the loan. Well, let's say I load in the data of my entire bank, of every customer I've ever had, and whether they defaulted on their loan or not. And that's going to be my predictor for, are you going to give Chris Eaton a loan? Now, it might be the case that some branch manager in the town that I live in doesn't like, guys with blue eyes, let's say. And so every time someone comes in with blue eyes, that person gets denied because that person has a bias. Now, that's just data in the database. And no one's going to notice that probably, because on average, blue-eyed guys like me get loans all the time, all over the country. But in this one little location, they don't. So overall, there's no bias. But in this one spot, there's bias. And now I go and feed all that data into my learning algorithm, and it learns how to be biased. It learns how to get blue-eyed people that live in Whitby in Ontario to not get loans. And so I go in to get my loan and it says, what color are your eyes? Blue eyes? Oh, you don't get a loan. It's like, why not? Well, we don't know. It's a machine learning algorithm. Right? So that's the other part of machine learning that is a problem. Is one is biased. Two is, in most industries, regulated industries, you have to be able to, you can't just build a machine learning algorithm that just is a black box and that lets people just make decisions based on data, you actually have to, in a lot of regulated environments, have to be able to explain why you made that decision. Okay, so that's another aspect of the machine learning business that a lot of researchers are focused on, is how do I interpret the data? How do I figure out that Chris Eaton didn't get a loan because he had blue eyes? Right? That's a tough problem to solve, especially as you get into some of these very advanced algorithms that I'll talk about. And B, how do we spot bias in the output? Some people will say, oh, the algorithm's biased. No, the algorithm's not biased. The data you fed in was biased. And so it learned how to make a prediction based on the data it was given. So if your data has bias in it, and there's probably not much data that doesn't have some kind of bias in it because it's based on human nature, your predictive algorithms are going to have bias. So you need to be able to spot that bias, figure out where that bias is, and correct it somehow. Put in some processes to correct it. But it's really about trust in the data. So I kind of summarize in this part. What is machine learning used for? Well, it's used for identifying patterns in data and predicting some value out. So, do I give this person a loan? Yes or no? What should this house price be if I want to put it up for sale? And I should be able to look at all the houses that have sold in this area and what their characters are and build a predictor that says, okay, this house is worth this much money. Okay? And it really involves a lot of statistics, a lot of math, and a lot of calculations. So why haven't we done this before? Well, there's been limited success in the past, and for two reasons. One is the computing capacity. So we're at a point now where we have sufficient computing capacity to be able to build these complicated models and execute them. The other thing is CPUs are very good at doing one thing at a time. Okay, yes, we have a lot of parallel processing going on. We have multi-threading going on and all kinds of other stuff going on. But really, at the core of the CPU, it takes data and an instruction, processes it, spits it out, takes the next data, next instruction, process, just keeps doing that over and over again. So it does one thing at a time very fast. And yes, I can do multiple of those going on at the same time. But what you'll see a little bit later is what machine learning needs is I need to be able to do matrix math on the matrices, and I'll talk about that in a minute, very fast. And what's good for doing that is GPUs. So you go and you buy a home PC and they charge you a fortune for some graphics processor in there if you want to do gaming. Right? You want to play games, they charge you a lot more for a really good graphics card. Why? Because it's full of GPUs, and there's thousands of GPUs in one of those cards. Imagine a computer with thousands of CPUs. Right? It's crazy. We wouldn't have that. But these cards have thousands of GPUs on them, and what they're good at is doing parallel operations very fast. Okay? So I do 1,000 GPU operations per cycle. And what they're doing in gaming is figuring out what the color of the pixels should be. Right? I've got this huge matrix of pixels, and I process this information through the GPU to play my games. Well, with machine learning, imagine I've got a huge table of data. It's just a matrix of data. Right? And I want to process it all really quickly and look for correlations and look for patterns. Well, I can do that really good on GPUs than I can on CPUs. I can do a lot better on GPUs than CPUs. And so the addition of very good, high-performing GPUs is actually one of the reasons why machine learning is taking off right now. Okay? The other reason is there's a lot of good open-source frameworks. I'll talk about what that means in another couple slides. But open-source machine learning frameworks, areas where I can go and build my machine learning, is advancing as well, really well. So that's part number 2. And part number 3 is to build a good model, I need a lot of data. Well, what are we all swimming in right now, or maybe drowning instead of swimming, is data. Right? We've got so much data. And so all of this data makes my models more accurate. So I've got more data, I've got GPUs, and I've got the software to build it. That's what's making it take off right now, okay? Or enabling it to take off right now. So let me step back and talk a little bit about something that we all know very well, data types. And because there's different things for machine learning than there is for SQL, for example. So we have our typical structured data. And in this instance, this is really good for machine learning. Not so much deep learning, but machine learning. I use my regular rows and columns. Okay? And so, for example, I might have a banking information, and I want to figure out, is this account going to default on its loan? Here's all the payments for that person's made in the last 3 months. Here's the bills I gave them in the last 3 months, and are they paying or not paying? So that kind of information, structured information, is great for machine learning. Okay. Of course, this is where we all shine in our database space. A lot of data for machine learning is unstructured. So voice recognition, that's a classic machine learning problem. Image recognition, that's a classic deep learning problem. These are all really unstructured pieces of data that machine learning algorithms love. Right? Facebook, Twitter, the text that someone writes. I want to understand what's the sentiment of this person. Are they likely to, if I call them right now, are they likely to take an offer of an airline seat, for example? Well, if I am going through all of their Twitter data and finding out they had a real problem with, I don't know, let me pick one, Delta. Maybe if I'm American, I want to go and make them an offer because I just analyzed all their data and I find that they have a bias against Delta or against American, or whatever. And so looking at this unstructured data can make really good money-making predictive models. And then there's semi-structured. I kind of think of, I mentioned Twitter. Twitter is, the payload is unstructured, right? It's text, it's sentences, sometimes not even sentences. But that's the unstructured piece. But around a tweet, there's a lot of structure, right? Who is it? Where is it from? What are they talking about? All this, these hashtags have structure to them. So we call this sometimes semi-structured because there's a lot of information I can get out of the envelope that's coming to me, and the payload inside might be unstructured. Okay, so I do a lot of machine learning on that as well. Now, there's different types of training that I can do. And you'll hear a lot of this when you're talking to someone who's doing data science. The first is called supervised learning. By supervised learning, what we mean is, let's say I have a table. I want to pick one of those columns as the column that I'm going to predict. So in this case, I've got 3 columns, and the column I want to predict is this one here, true or false. Right? I don't know what these are. Maybe it's payments on a loan, and I want to predict, are they going to default or not, true or false. Or I have a bunch of images, and I'm telling it, these are all images of Dairy Milk chocolate. Okay? So I'm telling the system what these things are. And I'm telling it, these people defaulted and these people did not. Go and figure out what the pattern is. That's basically the objective of machine learning, is I give you a bunch of data, I tell you the expected result, and then the computer goes and figures out what data leads to what result. Okay? That's supervised learning. And I think of this as, I have 2 teenagers now, but when they were little, I did a lot of supervised learning, right? Especially when they were really little. They were like, I'd say, that's a dog, and they'd go, dog. And then I'd say, that's also a dog, and they'd go, dog. And then they'd point to a horse and go, dog. And I'd say, nope, that's a horse. But to them, it looks like a dog, right? It's got 4 legs. It's a really big dog, maybe. It's got a head, looks kind of doggish. It's got ears and a tail. Maybe it's a dog. So that's supervised learning. That's basically exactly what we're doing in machine learning. We're saying, that's a dog, that's a dog, that's a dog. And then it makes some prediction, and I say, nope, that's wrong. It's this. Or maybe I say, yep, you're right, that's a dog. And the child learns what a dog is versus what a horse is based on how I interact with them. And that's what supervised learning is. The other aspect is unsupervised learning. And here, I don't have any labels of information. And I'm telling the machine learning algorithm, you go figure it out. I don't know. Go figure out if there's patterns in this data. So it might look at this data and find patterns that I didn't even ask for. Or it might find here, this is a bunch of data, and I might say, well, I want to see all the pictures that are blue. And it'll come and start looking at, oh, okay, well, now I want to understand color. So it starts organizing the data by color, or maybe it organizes it by shape or something else. It just looks at the data and starts clustering things together and say, here's a pattern I found. So that's unlabeled or unsupervised learning. Okay. And the third one is called reinforcement learning. And we probably won't find this much in the database space. But here, this is a machine learning type where I don't tell it what to do. I just tell it whether it gets a reward or not. And I kind of think of this one, maybe the unsupervised one, well, maybe reinforcement learning is a good one. When my kids play with Lego, there's no right or wrong when playing with Lego, right? First they eat it, right? And they find, nope, it's not tasty. And so no reward there. Sometimes maybe, I don't know, maybe it is tasty. It helps with the teeth or whatever. But then they start, playing with it, and then they stick two together, and the eyes, when they stick, right, it's like, wow, two pieces stuck together. They got a reward. Something happened, right? That's reinforcement learning. So I am training a model by giving it some reward when something positive happens, and I give it some penalty when something wrong happens. So in the case of identifying chocolate bars, right, when it identified three correctly, I give it a +3. For the 3 that it got wrong, I give it a -3 and say, oh, I'll try again. Okay? This is used a lot in game simulation. So my son right now is building a machine learning model. You know the game Snake, where you just use the arrow keys and the little dot goes around, tries to eat the little berry, and when it does, the snake grows and it keeps growing, and you can't run into itself. And he's using it to try and build a reinforcement learning model that the computer itself is going to learn how to play Snake all by itself. What it's going to do, it's just going to move. And it's going to just move in a random pattern. And when it hits the berry, it's going to get a reward and go, oh, I'm supposed to hit the berry. Okay, got it. And when it hits the wall, it's going to get a penalty and go, oh, I should not hit the wall. And so it's going to learn, after a while, it'll just get the berry every time, and the snake will keep growing. So that's reinforcement learning, is that you give it a reward for doing something good, you give it a penalty for doing something wrong, and let the computer figure out the best way to play the game. That's why I say probably not the most useful for databases. Right? We're not going to have a lot of, hey, just go and figure out how to access the database and look for rows. Not so useful in that case. Okay, so now I've got some learning model that I want to use. How do I get the data to it? Okay, so in machine learning, I take all of my data and I have to break it up into sets. Okay, because I have to take some data and train a model. And I'll talk about what a model is. That's probably one of the first things, but just use it in abstract for now. So I have a set of data that I use for training, okay? And I have a set of data that I'm going to use for testing. So let me take an example of, I'm going to build a house price predictor for real estate. I'm going to go and predict what the price of a house should be. I'm going to take all of the data of all the sold houses in a certain area, and I'm going to take all that data and I'm going to put it into my model. Well, if I took all the data and put it in and built a model, I don't have any more data to go and test to see if it's any good. I have to wait until some other house sells to see if I was right. So what we usually do is we break it up about 80% for training, about 20% for testing, randomly break up the data, and load the data in, create a model that's going to make some prediction, and then I go and I score it on that test data. So I throw in test data and it says, okay, I predict the price will be here, and then you see how well your model's doing. That's what a data scientist's job is. Build a model and see how it does. Okay? There's another section that isn't often talked about called validate. And what this is part of the training data I pass into the algorithm. That algorithm will use part of it not to train the model, but to see how it's doing as it's going through its training. Okay? This test data I do at the very end. The system says, here's your model. It's beautiful. I love it. It's really good. And then I take the test data and see how good it did. As part of training, there's this data that I use to validate as I'm running through. Am I doing a good job here? Am I getting it right, getting it wrong? So there's sometimes, and the very confusing thing, if you read a lot of literature, sometimes data scientists call this the test data. It gets very confusing. But the idea here is there's a lot of data I'm using to train a model. Some of it I'm validating as I'm training. And then there's test data I use afterwards. So when you see that, when you're learning machine learning, be aware of that. Yeah.
So I get the 80 point for train versus test.
Yeah.
So is there a rule of thumb for the amount of data to keep for validate?
So usually a machine learning algorithm will use 20% of the training for validation, sometimes 10%. There's a part I'm going to talk about a little bit later called hyperparameters. And the first time I heard about this, I had no idea. What's a hyperparameter? Why is it hyper? All of these things, how much percentage I'm going to use for training, how many times I'm going to go through the training, are these things called hyperparameters. And data scientists spend their time, a lot of time, tweaking these little numbers. Okay? They'll run a test. They'll go and change some of these numbers. They'll run another test, change the number. So I might save off 10% for validation, and that's a hyperparameter I specify when I build the model. And then I find out the model's not very good. So I might bump that up to 20% and then run the model again. And so one of the things you should know about machine learning is it's a very iterative process. They do it over and over and over and over and over again. So if you can save any time building a model, run it on more GPUs, a faster server, whatever, that savings becomes exponential when I'm actually doing this in practice, because I'm doing it over and over and over and over again. So I save 10 seconds, I run the model 1,000 times, now I've saved 10,000 seconds. So little increments can be a big thing. It's not like SQL. You run a query, and then, okay, I got the answer. No, I'm going to run it again to see if I get the same answer, kind of, in AI. It's kind of like that. So one of the things that is a challenge for AI is the complexity, and that's why the amount of data is important, and I'll show you why. So, there's dimensions to data. We're all familiar with 2D images, right? The graph is a 2D image. These are 3D images. Right? This one obviously looks 3D. This one is 2D, but the size of the bubble is the third dimension. Could determine what, how much of a particular quantity I have on hand or something like that. It's really hard to visualize much past 3D. I got a good 4D one, so that's this one. So that's a 3D image, but with color. So that's the fourth dimension here. Right? But in reality, we're not visualizing, but actually working with, you are all experts in multidimensional data. Why? Because that's a 9D piece of data, set of data. Okay? I've got 9 columns. There's 9 dimensions in this table. But we don't talk about it like that. But you are already multidimensional specialists. So put that on your resume. See, yeah, there you go. Someone's already writing it up. But this is the problem. So when I'm looking for patterns, let me go back to this one. If I'm looking for a pattern here, okay, I can actually see there's a pattern, right? Starts off like this and goes up like this. So I can see the pattern in 2 dimensions fairly easily. I can see some pattern here, right, in this 3D map. Anybody see a pattern here? Really hard to find, because I have to look at every column in combination with every other column to see if there's patterns. Okay? And so as I add more columns, I need to add a lot more rows. Because if I just had 2 rows here, right, there's no I can't find a pattern with 9 dimensions and 2 rows. I need more data. So the more dimensions I add, the more things I'm looking at. So in the case of the house example I gave you, well, there's number of bedrooms, number of washrooms, lot size, is it a 2-story, is it 1? The more elements that I add in terms of dimensions, the more data I need to put into the model to try and look for patterns. Right? If I just had all houses either had 1 bedroom or 2 bedrooms, that was it. Okay, well, it would be easier to find patterns in the price of 1 bedroom versus 2 bedroom. But if I got bedrooms plus washrooms and finished basements, not finished basements, the more columns you add, the more data I need. So that's why it's becoming more popular now, is we have more data. So we're actually able to build more accurate models because we have millions and millions and millions of rows. Okay. Now, there's some math involved. We're all familiar with scalars, right? Scalar functions. So substring is a scalar function. Why? Because it takes a single value and does something to it. So a scalar is an individual number. A vector is a set of numbers. Right? You could think of this as an aggregate function, like min, max, average that we use in SQL, all work on vectors. Vector is the math way of saying, multiple values, okay, in a single set. Now, if I go to multiple values across multiple rows and columns, like a table, that's a matrix. Okay? And that's what GPUs are really good at, is doing matrix math. I don't know if you all remember back in, first year calculus, maybe it was, I don't remember. We did a lot of multiplying of matrices together. You have to, I can't remember. I know you have to take like the first number multiplied by, I don't remember how to do matrix math. But computers are really good at it, and GPUs are stellar at it, manipulating two matrices, doing math on two matrices. And that's why data science is so good using GPUs, and they focus a lot on matrix manipulation. And then a tensor is a matrix of matrices. Now, how many of you have heard of TensorFlow? Okay. That's where the name TensorFlow comes from. It's working on tensors. Okay. I didn't know what a tensor was. I thought it was a bandage you put on your arm when you got a sprained arm, right? A tensor bandage. But it's a matrix of matrices. And so if you think about like an image of a dog or a cat, right? It's a bunch of pixels, all have some set of values. I could represent that as a tensor. Okay? And then I do manipulation on that tensor. That's what TensorFlow is doing. So these data scientists are working a lot with matrices, and they're working a lot with tensors. I've been doing it for a couple of years. I don't do any of this. I just use the tools that do the work. Okay? So I'll show you the easy tools, but just so you understand where the word tensor comes from. So what's a task in machine learning? Well, you've probably done a lot of this without even knowing about it. Let's say I have data that represents this, right? Oops, sorry, I should use the arrow button rather than the... Right? I have data that looks like this. Well, I go and I use a linear regression to just plot a line through that data. Right? And now I have, if you tell me you come in with a value of 20, I'm going to say, well, your predicted result is 11, because it's right here. Right? That's a linear regression, and that's one of the very common used machine learning algorithms. Right? Just linear regression is a machine learning algorithm. Now, what happens over here? Well, linear regression is no good with this data, right? Because the straight line doesn't actually predict any of these values except at the two ends. So linear regression, not good in this case. It's useful for things that are highly correlated. Okay. Now, there's another concept. Let's say I have that same data, but my machine learning algorithm goes and says, okay, I'm going to go and build a predictive algorithm for that data. And I go and I build this algorithm that creates this crazy plot, right? Well, it looks great. Look, it's exactly predicting almost every single value. That's what we call in data science is overfitting. Okay? This model is overfit to the data. It maps exactly to the data. Now, that's not what I want, because if I come in with a random number, I want to make a prediction. And just because this data is down here doesn't mean that the next random number where I give 20 is not going to come in here. It just happens to be the data that I've given you. So you want something that fits well but doesn't overfit. Okay? Same for underfitting. This doesn't fit this data very well at all either. Right? Now, what does this matter, or why do I need to care about this? When I build a machine learning model, I tell it how much time to work on it. That's one of the hyperparameters, is how much time it should go and off and think. And it's called either number of epochs or the number of iterations. And if I give it too many and let it just scan at the data forever, it'll end up doing this. It'll find the perfect line that matches every single one of those data points. And if I don't give it enough time, it'll end up like this. Okay? So I did it, and how do I know what's enough time? You don't. Trial and error. And that's why data scientists spend all their time iterating over and over and over again to see, are they underfitting, are they overfitting, is the model scoring correctly? There'll be tools in the future that'll do this for me. There's already some coming out now, but right now it's a trial and error type of idea. But that's overfitting and underfitting, so two good things to learn. There's other machine learning tasks. I won't go through them, but one is called polynomial regression, so that's making a curve. The other one that's very popular is called logistic regression. And logistic regression is basically, give me a set of data, and I'll give you an answer that's either yes or no. Does this person get a loan? Yes or no? Should this person, is this person going to buy this car? Yes or no? Should I put up this ad in this person's Gmail? Are they likely to click on it? Yes or no? And that's logistic regression. It's actually the most used data science algorithm today. Out of all data scientists, most of them are using logistic regression. So just something to be aware of. There's another one that you'll hear used called k-means clustering. And so let's say I have this data. Well, a machine learning algorithm, if I tell it to use k-means clustering, it'll say, okay, well, let me try and find clusters here. And it might come up with this. Here's a cluster, here's a cluster, here's a cluster, here's a cluster. I think these things are alike each other. Okay, it'll build these clusters for you. And then it's called k-means because it'll then give me the average of each cluster. So you can say, if Chris Eaton is in this cluster and I don't know much about him, he's probably somewhere around here. There's the average of that cluster. Maybe this is, this is a cluster of people 50 plus who own their own home, and how likely are they to actually buy this brand of car? How close are they to the average of this cluster? That's something k-means clustering. And it's a type of, I talked about earlier about unsupervised learning. I'm not telling you what's going on here. You're finding clusters for me. The machine learning algorithm finds the clusters for me. Okay. Yeah.
So when do I decide that I've fed it enough data? Or is this learning this number as well in trial?
So in all of the cases, machine learning, it's probably the case that, I'll show an example when I do the demo, but it's mostly the case that you can never feed it too much data. Okay? At some point, it's not going to get any better. Its predictive algorithms aren't going to get any better. And what you look at is something called the loss function. So what the machine learning algorithm is basically doing is it'll come back and it'll make a prediction. Let's say it's doing the house price predictor. It's a good example. So it'll say, I predict this house will be worth $500,000. And then it looks at if you're doing supervised learning, it looks at, it only sold for $450,000. So I was off by 50K. And it goes and it adds up all of the how far it was off, and that's called the loss function. So if I'm off by 50K on this one, I'm off by 20K on this one, what's the average that I'm off by? Okay, that's the loss function. And over the iterations of the time that it's actually going through, you want the loss function to get lower. Okay, so at first, my loss function, because I'm making random wild predictions, might be off. Maybe my house price predictor is off by $100,000. And over time, now I'm getting down to my house price predictors within 20K, maybe within 10K. So once you see that loss function get to a point where that's acceptable for my business to say, okay, I'm off by plus or minus 5%, or whatever the case might be, that's when you've done enough. Okay? But sometimes it's not always just the data. It's tweaking all of these parameters. And sometimes if you give it too many columns, that's a bad thing too. Because I showed you, the more columns I have, the more data I need to feed it. So if I give it too many columns, that's another problem. And that you'll hear the term feature engineering. Feature engineering is a fancy way of saying how many columns should I use in my select query. Right? Each column is a feature. Now, sometimes I might manipulate the features, and data scientists do this all the time. So say, for example, I have a timestamp column. Okay, well, the timestamp of an actual house purchase is not that important. The day is probably important. The month is important. But the actual hour, probably there's not a pattern in the price of the house and the hour it was purchased. So they'll actually take features and manipulate them. Maybe they want to look at the day of the week of that column. That day of the week is not actually a column in the table, but I can go and write a query that gives me the day of the week. And then I feed that into my house price predictor. Maybe houses on Monday sell for more than houses on Sunday. I don't know, just guessing. So that's feature engineering. You can put that on your resume too. You're schooled in feature engineering. All right, so deep learning. What's the difference between machine learning and deep learning? Well, deep learning has been around, actually started in the late 50s. Someone tried it and had some success. It wasn't actually deep learning at the time. It was a simple neural network. But the idea here is they wanted to build a computer to mimic the human brain. Right? What does the human brain do? Okay, it's got a neuron inside there that a signal comes in and it decides, okay, it's going to fire and it's going to send off a signal to some other neuron. And they're all going to be connected and they're all going to, basically, that's how I think. I don't know, I'm not a neuroscientist, but I see these pictures of, looks like this. A signal comes in, it decides what it's going to do and fires off some signal on the outside. That's what this is trying to represent. Right? All of these, you think of them as neurons. Information comes in, it decides something, and spits out something to a bunch of other neurons that are all connected to it. Okay? So that's why it's called a neural network. It's a bunch of operations that are connected to other operations doing something. Okay? And each layer in this neural network is doing something. Okay? Let's say I want to determine, is this a picture of a cat or a dog? So the input layer takes the picture, and the next layer down might maybe it strips out all the color, just to look at black and white, because color can sometimes confuse algorithms. So it does that operation, spits it off to the next one, and thinks, okay, this operation now looks at, does it have whiskers or no whiskers? The next operation says, does it have, I don't know, is it got a tail, no tail, kind of thing. But I'm not telling it to go look for those things. It's trying to find these patterns as it goes through the data, and I'll show you that in another slide. But that's what a neural network is, and it's called deep learning because there's more than one layer. That's all. Deep learning is a neural network with more than one layer. That's it.
But is the flow still on one direction?
So not exactly. I'll show you that in another slide. The flow is I put a picture, when I'm done, I put a picture in here, and out the end spits prediction. Okay? When I'm learning, I go back and forth in the layer, and I'll show you that on the next slide. So I put in some values, and out pops some values. That's what a neural network does. Maybe it's relational data, maybe it's text, maybe it's an image, and out the other end pops some predictions. Okay? Now there's different types of neural networks, and so you'll hear these words, convolutional neural network. If you hear the word convolutional neural network, it probably means you're doing image processing. That's what they're mostly used for. This is an image of maybe it's a cat or a dog, and what I'm doing is I'm looking at subsets of that data over and over and over again, passing it through the machine learning algorithm to find out, is this a cat or a dog? That's called convolving. I don't even know what that word means. I didn't even know that was a word. But that's where you get convolutional neural network, or CNNs. So if you hear the word CNN and someone's saying, hey, we want to build a CNN, I hear you're the database guy. Like, yeah, you probably don't want to talk to me. I'm relational. I don't have images. This is mostly processing images. Okay. Recurrent neural network is another one, and this one is where I'm going inside the network. I'm actually looping back on top of myself. And this, if you hear the word recurrent neural network, think of it's probably processing text. Text to speech, speech to text, maybe sentiment analysis. They all use recurrent neural networks. And the reason is, when you think about it, it's kind of simple. If I say, I swung the bat. Okay? Bat has a meaning in that sentence because of the word swing. Okay? I probably didn't grab something that has wings and swing it. Okay? But if I just give you the word bat, half of you will think of a baseball bat, and half of you might think of a flying bat. Right? But if I say I swung the bat, probably no one thought of me grabbing a rat-like looking thing with wings and swinging it. Everybody thought I swung a baseball bat because the context of the words matters. And that's why recurrent neural networks are so good for text, because it can go through the word and it sees the word bat, and then it backs up 2 words and says swing. It's a baseball bat. I didn't tell you it was a baseball bat. I just said I swung the bat. Okay. So recurrent neural networks are good for text processing because text processing has meaning between the words. Okay. So this is this is as deep as I think I'll go in terms of machine learning in the beginner section. But the idea here, the way this works, the way a neural network works is I've got those input layers. Okay? I've got some layers in the middle, and each of these layers has something called a weight on it. Okay? I start off with a weight of just 1. Everything is 1. And this is how it learns. I start off, the weights are all 1. I pass in a picture of a cat, and it does something to it, and out at the end, it either pops the word cat or dog. And if it pops out the word cat, what I do is I go and reinforce, I increase the weights of every one of these lines that thought it was a cat, because it came out with the right result. Okay? If I put in a picture of a cat and it does its processing and out pops the word dog, then what I do, what the machine learning algorithm does, is it'll go back and reduce the weights on all of these lines that thought it was a dog. So basically, when it gets it wrong, I reduce the weights of the ones that influenced me to get it wrong. And when I get it right, I increase the weights of the sections of that brain that thought it was right. Okay? It's probably what's going on in your head when my daughter points at a cat and says dog, and I say, no, that's a cat. Something in her brain is rewiring itself to say, oh, that's a dog, not a cat, or whatever the case is. So that's what's happening in this neural network is there's a bunch of numbers, and I'm increasing them or decreasing them to strengthen or weaken these bonds that are making it decide what it's going to be, cat or dog. Okay? And that's why matrix manipulation is so important here, because really this is stored as a matrix, there's another one stored as a matrix, and I just start mashing them together, adding them, subtracting them, increasing and decreasing. And so the way I build a model is I go through this over and over again. I send in a bunch of data, it goes and builds this neural network with all these weights, and then I do it again, and 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 eventually my line starts to map to what the data looks like. That's why I go over this over and over and over and over again. And each of these is called an iteration, or sometimes called an epoch. You'll see that word used sometimes as well. And every time I go through, I look at the loss from the previous run and try and correct it by changing these weights and biases. Okay? And to your question earlier, do I go through this once? Is it a one-way street here? When I have my model and I'm making predictions, it's a one-way street. But when I'm building it, it's a two-way street. And what I do is I go through and I train and I calculate the result and the loss, and then I go back through the model and fix up all these weights to try and make it better. Okay. I don't do that physically. The algorithm does it for me. That's what all these frameworks are doing for me. TensorFlow, Caffe, they go and they change the weights, and they learn themselves what the weights should be for the actual algorithm. But that's what deep learning is. And there's a term called backward propagation, where I'm going back through the network to fix things up. So what have I got in the end? I have this neural network. I have this thing called a trained model, which is basically this neural network with all the weights on it, so that when you give me something, I can make an accurate prediction. Okay? There's these weights and biases are all fed in, and this is a model. Okay? I can then go and take that model and use it somewhere in my application or wherever to go and make predictions based on new data that comes in. When new data comes in, I run it through this, apply these weights and biases. Out comes a prediction, and I say, he gets the loan, he doesn't get the loan. Or I say, the house is worth this much. Okay? Now, what you have to do, though, as a data scientist is, well, things change, right? House prices change. So I have to go and keep retraining this model to be accurate, and over time, it'll start to degrade. And I have to go and detect that degradation and retrain my model with new data. There's some areas where you have to do that, some areas where you don't. So for example, if I'm detecting lung cancer in scans, right, what lung cancer looks like probably doesn't change very much. Lung cancer looks like lung cancer. I don't know what it looks like, but I'm sure someone who's an actual doctor, cancer doctor, will know what lung cancer looks like, and they'll be able to diagnose it by seeing it. Those models don't need to change much, right? Because it's not going to change. Next week, lung cancer is going to look like lung cancer today. But house prices change all the time. Stock prices change all the time. And it could be because of some other influence that I'm not including. So that stuff needs to be added in. Now, there's these deep learning frameworks that you hear about, TensorFlow, PyTorch, Caffe, Keras, now part of TensorFlow. All of these are what make data science a little easier. Okay? Think of it like an application development environment where I'm using these already built APIs or already defined infrastructure to go and build my own model. And almost all of them are open source, so that's why it's also taking off quite a bit. So how do I make use of a trained model? I kind of talked about this. I take a picture, I run it through some API, it calls the model, that spits out a result. So in this case, it spits out a success. This was the image you gave me, and I think it's a cream egg, and I'm 94% confident it's a cream egg. Okay. The quality of the results is defined by the accuracy, and there's two different things here. There's accuracy, which is how often is my model correct, and then there's confidence, which is for this one image, how sure are you that it's actually a cream egg or a Jersey milk or whatever the chocolate bar is. That's confidence, and this is accuracy. Okay. And data scientists spend all of their time looking at the accuracy of their models and trying to figure out if they need to go and retrain their models. Okay. Images are interesting, although not as useful for relational data, but there's different types of images you can look at. You can do image classification, which says, okay, this is a picture of a cat. Or I could use classification that says, this is a picture of a cat, and here's the cat inside it. There's another type of image recognition called object detection, which is, okay, this is a picture, but here's a dog, here's a duck, and here's two cats. Okay, so it's identifying where in the picture they are. And then there's something called instance segmentation, which is looking at, okay, here's a dog, and here's the outline of the dog. Okay? This is used a lot in autonomous vehicles. because they get a picture of the road in front of them and they segment it into, don't hit these things, okay to drive on these things. And that's basically autonomous driving in one sentence. So let me give you a little demo. Are there questions while I'm switching to the demo here? So I'm going to give you a demo first of the image stuff. Why? Because it's more fun than looking at rows and columns. So let me show you, this is a tool. There's lots of tools out there. This one's called Power AI Vision. It's a vision classification and detection tool. But here's how easy it is for non-data scientists to actually do this kind of thing. So what I start with is data. And then I've built all kinds of models. I've built, we're looking at free parking spaces in our parking lot in the lab. I've done some for sporting events. I haven't done one yet for basketball, but since I'm from Toronto, I'll be doing a sporting one for the Raptors soon, I'm sure. I looked at one for dented cars, pothole detector, sickle cell anemia detector. These are all easy. Let me show you what it does, though. So first thing I want to do is create a data set. And if you need to move up, I don't know if you can see from the back, but let me do a data set of dogs and cats, because that's easy. What this allows you to do is you don't have to be a data scientist to build this kind of model. You need to be a domain expert. Anyone who can recognize a dog or a cat in a picture, you're a domain expert for dog and cat recognition. If you're a cardiologist, okay, you can be a domain expert for looking at heart scans. Right? Okay, I couldn't do that, but someone can. And the cardiologist doesn't need to be a data scientist. So I've got this data set, and all I'm going to do is drop in pictures here. So I've got a bunch of pictures of dogs and cats. Here's all my cats. Let me, cat goes to here. Oh, that's a cat. So let me go and grab all those cats, and I drop them in here, and I add them to my data set. And then I have to tell the machine learning algorithm, okay, these are cats. Okay, so what I do is I select them all, and I basically say, assign them a category, and I say, this is a cat. Okay. And now I'm going to do the same thing for dogs. Let me go back and grab those dog pictures and drop them in. Add those in. And you'll see over here I've got one category of cats, and I've got a bunch of pictures that are uncategorized. So let me pick the uncategorized ones. And I'm going to tell the algorithm here, this is a dog. And that's it. So now I have 11 pictures of cats, 9 pictures of dogs, and now I'm going to go and train a model. So I click on train. I give it a name. There's 2 types of training you can do that. I talked about image classification, which is that one that says the whole image, what is it? And object detection would be, show me inside that picture where the dog and where the cat is. Okay, so I'm just going to do the simple one, image classification. Take all the defaults. And here's where I talked about those hyperparameters. Let me go down to the bottom here. So how many times am I going to go through and iterate over and over again to figure out if this is a cat or a dog? And there's a whole bunch of other things that data scientists worry about. How fast is it going to learn? Let me do something simple here. So that it finishes in a reasonable amount of time. And what it's doing now is it's going through all those pictures and trying to figure out, well, here's a picture that you said is a cat. Why is it a cat? And here's a picture you said is a dog. Why is it a dog? Okay, well, let me try and figure out, is there patterns in this data or no patterns in this data? And it'll figure it all out for me. This will take about, 30, 40 seconds. But while it's running, I mentioned earlier, how do you know if you have enough data? Most tools will show you this loss graph. Okay, and it'll show you, I started off and I was, not very good, and now I'm getting really pretty good down here. After 300 iterations, it's got it pretty well for those 11 pictures. Right? My accuracy is pretty much close to 1. So 1 is 100% accurate. Obviously, it's only 11 pictures, so it's not that good. But it'll create a model, and then I'll be able to actually deploy that model. Let me actually, it's finished already, so I'll do it. So now I can deploy that model, and I just give it a name and deploy it. But let me actually go back to my models here that I've run already and deploy this one. I'll call it deploy. And what deploy means is, let me use this in an application somewhere. So it goes and it basically sets up an API that I can call this model. Because the model itself is only good if I can actually call it from some other application. So here's the model that it created. It's got 91% accuracy. And if I click into it, here's the API. So if I actually call this API endpoint on this server, I pass it a picture of a cat or a dog, and it'll come back and say whether it's a cat or a dog. Okay? I can put that in. I can give that to my application developers and say, okay, go build your application. your cat-dog detector. But we have a little test tool here, so let me go into the test tool, and I'll take this picture of a dog that I didn't train on. This wasn't part of my training set. And it says, I'm pretty sure this is a dog. I'm 87% confident it's a dog. But, might be a cat. Not sure, 100%. 12%, maybe it's a cat. And this heat map actually tells me, for this dog, why do you think it's a dog? Well, because it's got this red spot here. This section makes me think it's a dog. This face, this nose, and these eyes is what's important. And I didn't tell it that. It just figured out, hey, all the dogs have a similar kind of spot right here. And so that's what I'm going to train on. If I go and grab cat, let me put the cat in there. Cat. It says, okay, I think this is a cat, and actually I'm really sure this is a cat. No chance this is a dog. And it's because of the facial characteristics here. The whiskers are a little bit bright as well. But these eyes and this nose, that makes me think it's a cat. And I didn't tell it any of that. It just figured out of those pictures, I think it's a cat. So that's how machine learning works. I actually built this one here, by using the same type of thing to track. This is tracking advertisers on the field, right? It's looking at. I trained it on Toyota, Emirates, Makita, and Kirin, and I said, whenever you see that, let me know. And it returns in each frame. It returns, here's that image. Okay. And I also trained it on the actual referee and the goalkeeper. And you'll see here when I see it's coloring in the goalkeeper. Let me go to the next phase. I also trained it on the goalkeeper. So in this case, what I did was I said, tell me when you see Toyota, and tell me when you see the keeper. And I used segmentation for that one to color them in. And I then built a little application in Python, very short amount of code, that actually goes and says, okay, every time you see Toyota, that's 1/30th of a second, because it's 30 frames a second. Go and tell me how long Toyota's on the screen. So I can go and now sell advertising as a service and say, whenever your image is on the screen, I'll charge you for it. If it's not on the screen, you don't get charged, which would make an interesting service model. But you can see the keeper's all nice and pink here. So that's the kind of things you can do with images. Unfortunately, we don't have enough time to show you the relational piece, but there's lots of tools. Watson Studio was being shown over in Mark Ryan had a lab using Watson Studio. This is another tool. There's a couple other tools out there. This one's called H2O. It's a partner of IBM's. They have a tool called driverless AI. And the first time I thought about that, I thought, oh, you mean you don't need a driver to connect to the data? It's not that kind of driver. They're talking about a driver of a car. So this is driverless AI, meaning you don't need a data scientist. You don't need the driver. It's driverless. It really confused me because I'm like, well, how do I get at the data if I don't have a driver? And I'm like, no, we're talking about driverless AI. But this is a tool that will do the same kind of things I just showed you for images. It'll do it for relational data. So I train it on, so I take data that I want to train, and I see, this is actually Titanic data. So this is a data set, had all the people on the Titanic and whether they survived or not. And then you can use this to build a tool to predict who's going to survive and who's not. And you can put your own name in there and what class you want to be in, how much you want to pay for your ticket, and it'll tell you whether you would have survived the Titanic or not. Okay. And so you see, did they survive, did they not survive? If I go back, there's actually correlations in here. I can go and look at, if I visualize the data, they have a nice way of looking at the data. So what's correlated with what? If I go up here, I can look at, if I can find survive. Here's survived. So survived is correlated to gender. It's correlated to my class, what class I was in. And actually, it's correlated to where I embarked. So if you left out of Southampton, you had less of a chance than if you left out of Ireland when they picked up other people in Ireland. I guess they picked the rich people up in Ireland. But then you get these experiments, and you can actually go and use them to predict who's going to survive and who's not. And there's some videos out there if you want to see this, but basically it takes all that data, builds a model for you. You don't have to tell it anything. It goes, looks for patterns, and then spits out, here's what I think is who's going to survive and who's not. If you want to look into this in more detail, I only got a minute left, so there's a site called Kaggle, Kaggle, Kaggle. Google that. Kaggle is a data science community. So think of Kaggle as the IDUG for data scientists. Okay? And they have all kinds of tournaments, competitions, where they'll put out a data set, and they'll say, we want you to predict X. And whoever gets the closest, the best predictor, they win a prize. Sometimes the prize is just you get to be the Kaggle Grand Master. They actually have these levels. You get points. And you work your way up to Kaggle Grand Master. Then you put your name on. The prize is you put Kaggle Grand Master on your resume and you start making way more money. That's the prize. But sometimes companies will put out challenges out there with money prizes. They'll say, we're looking for a new way to, predict wear on our turbine. And here's the data, and if whoever comes up with the best predictor, we get to use the algorithm, and you get $50,000, something like that. So I used H2O, the driverless AI, to try and make some predictions, and it does a good job, but it's not as good as a Kaggle Grand Master. But it can get me not to the top of the list, but not enough to win money. But yeah, so there's, this is using all relational data to make predictions. There's image tools to use image to make predictions. The key for relational database, I think, is going to be every data scientist is going to want to suck all the data out of your tables. So be ready for that. There's not a good way to do data science inside of the tables, right? Because I'm doing all this manipulation of the values. By the way, data scientists don't like text. So all of your tables that have text, they hate it. They just want numbers. In fact, they'll take a text string. Let's say I have a column that's gender. Right? They'll take what they'll end up doing is breaking that into two columns. Is it male? Is it female? And it'll be zeros or ones. Okay? It's called one-hot encoding. And they love this because it makes it easy for math. But the problem with, if I take a column and make it, okay, 1 is male, 2 is female, or some other column that's, has 7 different values in it, I go 1 to 7, machine learning algorithms think 7 is better than 1. It thinks it's 7 times better than 1. So that's not good. That's why they use this one-hot encoding, so it's either 0 or 1, true or false. So they'll want to take all the data out of your tables. They'll want all the data converted into just numbers instead of character strings. They don't like decimals either. And so expect that. Be ready for that. Have some easy ways to get them data. And then the second thing is, once they've built the model, that's where we come into how do I get that model into a stored procedure so people can call it? That's the key, I think. So think about, learn how to build good stored procedures, and you'll be able to take their models and embed them inside your database, and then you have control of the model because it's inside your database. So with that, that's the end of the conference.